Are you feeling energetic? This is the fifth and final video in the motion physics series, Energy. You may have watched other videos in this motion physics series with all of this talk about moving things, but never a mention about energy. What is energy? Well, it turns out that work is energy. So Newton meters, or joules, are a measurement of energy. Remember joule and watts, or joules per second? That's how much energy there was in an amount of time. That's power. There are two basic forms of energy: kinetic, which means moving, and potential, or not moving. Energy is the ability to do work. So, if something has the ability to move or cause movement, then there is energy present in the form of potential energy. Kinetic energy is calculated by mass times velocity squared, divided by 2. The velocity is squared because it matters so much more than mass. Obviously, mass matters. When something has more mass, it's going to make more of an impact. An example of velocity being so much more important is realizing how much damage a small object like a bullet can cause when it gets moving faster than the speed of sound and penetrates walls or slams a body by its violent impact. And it's divided by 2 because it's being averaged over the beginning of its flight to the end, kind of like averaging speed when you go from point A to B in some time. The potential energy of something that falls, like a skier, is calculated by multiplying the weight by the distance that it falls. This is called gravitational potential energy. Another type of potential energy is elastic. This is when the potential energy is stored, used, and restored again. Examples are rubber bands, super balls, and shooting arrows with a bow. Probably the main thing to understand about potential and kinetic energy is how potential and kinetic energy can change into each other. They can cycle back and forth in moving objects like pendulums and roller coasters. When the roller coaster moves slowly up a ramp, it's gathering potential energy until it reaches the top. Then it has all potential energy and no kinetic energy. When it starts moving downwards, it's gaining kinetic energy and losing potential energy. Then when it reaches the bottom of the track, it has all kinetic energy and no potential energy. But it then starts building up potential energy as it goes back up to another high point in the track. So, where does that little 2 above the V come from? Why is the formula for energy m times v squared and not m times v like Newton's momentum? Émile du Châtelet in the 1700s began to disagree with Newton's idea that energy was proportional to mv, like his third law of momentum, but rather that it was mv squared, like Leibniz, Newton's co-creator of calculus, had argued. Back then, the word for energy was vis viva. It wasn't until 1801 that the term energy was finally coined by Thomas Young in a talk presented to the Royal Institution. Young allowed balls of varying mass but of the same size to fall from various heights into a box filled with tallow, which is wax. He then measured the amount of volume in the crater made by the falling ball and related this to the mass and the impact speed of the falling balls. He assumed that the volume of the hole created was proportional to the energy required to produce it. He correctly concluded from his study that kinetic energy was proportional to mass and velocity squared. This means that if you drop something from a height necessary to make the speed 2 times greater, the resultant crater will have 4 times the volume, and when 3 times the speed, then 9 times the volume. You should know that just because we say that the speed is 2 times or 3 times greater, that it's not the same thing as dropping it from 2 times or 3 times the height. That's because, don't forget, the speed of a falling object increases as it falls. Each year, my students conduct a lab where they are provided the formula final velocity squared equals initial velocity squared plus 2 times 9.8 times the height dropped. With this formula, they can then drop an object of the same mass from a height, then double and then triple it, and find out if the crater volume is double or triple or is the square. By counting drops of water, that fill the crater, they find that it is the square, just as Thomas Young found in 1801. These equations and measurements of energy were later used by Einstein and other famous scientists to equate matter and energy. Notice how E equals mc squared resembles Young's formula for kinetic energy, E equals mv squared divided by 2. And this is no coincidence.